Let me do this integral with the 5 different methods. So this is a very good example for those who take in calculus course, to practice different kind of techniques dealing with integral with sine and cosine. Okay, the first method, directly do it, without any treatment like substitution. So I multiply by the denominator and numerator by sine x plus cosine x and sine x minus cosine x. And the numerator will be multiplied by the same thing. Sine x multiplied by sine x minus cosine x. Okay. Good. I have to write it smaller to keep more space. So this is equal to, the denominator will be x sine x squared minus cosine square x. The numerator will be square sine x minus sine x cosine x dx. All right, good. This is equal to, the denominator will be negative cosine 2x. This is a half 1 minus cosine 2x, right? Minus 1/2, this is sine 2x dx. You must be good in trigonometry. And this, I'll take 1/2 out from numerator, and this is a negative. This is negative. This is negative. I can change it negative to positive, both top and the bottom. So this is a positive cosine 2x. Change it to negative, therefore becomes cosine 2x minus 1. This will be changed to positive, right? Sine 2x dx. We like working with positives. Now then, this is half the integral. This over this is a 1, right? This over this is a negative secant 2x. This over this is a positive tangent 2x dx. Well, so far so good. Then we integrate 1 by 1. This one is x. This integral is half log secant 2x plus tangent 2x. Now, you may have done that before, okay? If you haven't, then you may practice yourself separately, how to integrate the secant. And plus, there's no room for it. Tangent integral is a log, right? Log secant 2x, all right, plus c. Okay, so far the integral concern hasn't been done. The leftover just simplify. We simplify whatever it is. Okay, this is half. This is x. This is another common factor. Okay, this is square bracket, and the log This is secant 2x plus tangent 2x. Now things are taking negative out, so this is change of sign, becomes negative. So negative is going bottom, right? Secant 2x. Yeah. I have to write carefully, you know. Many times I just have absent-minded errors, so I have to work very carefully. Okay, now and then this is a half bracket x minus half log. This over this is a 1, right? This over that. You can simplify by multiplying cosine 2x top and the bottom. So you get sine 2x. Right. Okay. So this over this is a 1. This over this is sine 2x. Now this is equal to half bracket x minus half log 1. 1 is sine square x plus cosine square x, right? This is plus 2 sine x cosine x p plus c. And this is a perfect square, sine plus cosine square. So this is equal to half x minus half log sine square x plus cosine square x. No, sorry, square there. She have an error. Okay, this is perfect square, right? Sine plus cosine square. And this square cancels with this half. It becomes half x minus log sine x plus cosine x. Yeah, plus c. So that is the very answer to my integral in the beginning. Right. Okay. Method 2. This is sine x plus cosine x dx. Now, the second method is using substitution, right? That you should be familiar with it. We'll let t be tangent half x. Then we convert sine x, cosine x, and dx into t. Now, if you don't remember the conversions, we can derive, yourself by draw a triangle, right? This is a half x. This is a t. This is a 1, right? Tangent. Therefore, this is equal to 1 plus t squared. Okay, then we can find sine and cosine. And sine x is equal to twice sine half x, right? And the cosine half x. Well, I have to write it small because there's not just space. This is true. Sine x is equal to what? Sine x is a t over 1 plus t squared, right? And the cosine half x is a 1 over this. So this is equal to 2t over 1 plus t squared. You know, we get a sine x. We don't have to remember all the detailed conversion. Even if we forget, you can have it easily. And the cosine x is equal to cosine square over half x, right? minus sine square half of x. Half x, right? So cosine is equal to what? Cosine is equal to 1 over this. So this is 1 over 1 plus t square. And the sine square is a t over this, right? T square. Sine half x t square over 1 plus t square. So this is equal to 1 minus t square, 1 plus t square. So we get a cosine. Now for dx, because t is tangent half x, therefore half x is equal to arctangent t. If you differentiate both sides, then half dx is equal to 1 over t squared, right? dt. And therefore dx is equal to 2 dt over 1 plus t squared. See? You have a dx, you have a cosine x, you have a sine x. So we can do the integral. Now, this is the integral sine, well, I forgot, 2t over 1 plus t squared. Cosine is, I don't remember, 1 minus t squared, 1 plus t squared. Okay, this is cosine, right? Plus sine. Sorry, sine is 2t and 1 plus t squared, right? Okay, this is cosine, this is sine. And the dx is 2 dt of 1 plus t squared. Then multiply over 1 plus t squared everywhere, top and the bottom. You have a 2t 1 minus t squared plus 2t. And this one is 1 plus t squared, right? And dt. Okay. Now then what? I think it's partial fractions, right? Now I don't do the details of partial fractions. I suppose you know how to do partial fractions. Just write the result. Okay. This one is equal to 1 plus t squared plus 2t t minus 1 plus 1 plus t squared t plus 1 and dt. Okay, from here to here, I think you can fill up the details by yourself, partial fractions. Then we can integrate each of them. Now I have this derivative, right? This derivative is 1 minus t squared plus 2t is equal to negative 2t plus 2 and dt, right? What do we have? We have a t minus 1. So this one is equal to take negative half out. So this becomes t minus 1 dt, see? Do you understand? So I can write this for this. See? So my integral becomes 1 minus t squared plus 2t d 1 minus t squared plus 2t, and the negative half. Negative half for this one. Because you see, this one is equal to this. Well, the reason I'm writing this way because this result becomes a log, something natural log. Okay, plus t over this, dt, right? I can write 1/2 d1 plus t squared, right? They are equal, so plus 1/2 d1 plus t squared, 1 plus t squared. And there left another one, there's a plus integral dt, which is 1 over this, so 1 plus t squared. So I split this integral into 3 parts. This over this is this. This over this is this. 1 over that is this. Okay, each of them can be done. So the first one is a half negative log 1 minus absolute value minus t squared plus 2t. This one is a log 1 plus t squared. This one is arctangent, right? Arctangent t, yes, then plus c. So far as integration concern is done. We just need to simplify and put x back. Then let's do one by one. Okay, this one. Okay, let's see. This is a 1/2, right? 1/2. We have common log. This is negative. This is positive. So this becomes 1 plus t squared, right? 1 minus t squared plus 2t. Half, yeah, plus arctangent t plus c. So, okay, that's first we organize this one. And then now, if I switch numerator and denominator, it will be -1. Therefore, I'll leave -1 outside. Negative, this will be upside down now. Minus t squared plus 2t, 1 plus t squared. This one is a half x, right? Because t is a tangent half x, and plus c. Now, and then this is equal to 1/2 log 1 minus t squared over this is cosine. 2t over this one is sine. So this is sine x plus cosine x, right? Plus half x plus c, negative. Okay. So that is the same result as the method 1. This is method 2. So it's been done. Okay, you can go over now, if you see the video, you can go over by yourself. The only thing that the partial fractions, you may fill up the detail, from here to here, I'm using partial fractions. Okay, now method 3. Now method 3. Method 3 is using this complex numbers. Now sin x is this, right? Cosine x is that. And then we replace sin x and the cosine x by these two. So you get this. This is our integral. And then we replace sine by this, cosine by that. Then obviously that we multiply 2i to both numerator and the denominator. So it becomes this. This is a numerator. This is a part of a denominator. This is a part of denominator. Okay, then look, the denominator. Denominator has 4 terms, right? The numerator has 2 terms. If we add 2 more terms on the numerator and subtract the same thing again, that's a 0. This is 0, so this is still equal. Now the reason of doing this, because this over that is 1. Left over these 2 terms. Left of these 2 terms. And you take negative out, and these 2 terms become positive, right? Positive, because take negative term out. Now if I subtract this, add this, it's a 0. Add this, subtract that one, it's still 0. Therefore these two and make together is a 0. So the reason of adding these 4 terms, because of this. Now the denominator, this is denominator. This is denominator. The derivative of denominator will be equal to this. So this derivative is this derivative is this derivative is this derivative is this, right? Then times dx. Now if I can create the numerator like this, then it will become the derivative of a denominator. That brings our log function, right? Therefore, I do have this, I do have that, but I don't have this. But adding on this, I don't have this, I add on that. Then I subtract it. Then I subtract that. This is still 0. Okay? Then these 4 terms. These 4 terms together with denominator becomes this, because these 4 term derivative is this. So this becomes d this over that, and the leftover this over that. This over that is my original I. See, this over that is my I, which is the origin of the beginning integral. Therefore, this is I, because there's negative sign. Therefore, it's negative I. Then I move this I over there. I get 2 i's. Therefore, I is equal to half. This is x. This is the log, natural log of this, right? D something over something is a log something. So integration, the integral has been done, c plus c. But we want to change it back into nice result, right? Therefore, I add 2i here. This 2i I borrow from c. This is constant. I can borrow a natural log 2i. I can borrow natural log 2i negative. Well, I don't have to pay back because this is constant anyhow. And this This over that is sine x. This over that is cosine x. So that is my result. Okay, this is a method. This is a method 3. Now, because this method has a lot of writing and the tedious writing, therefore I present in this way, right? So this is method 3. Method 4. Well, let me make some points here. Okay, this is a sine x plus cosine x. This kind of integral, integral with trig functions. The above 3 methods are very commonly used. You can straightforward to integrate them, or you can use substitution, or you can use complex numbers. But furthermore, sometimes the specific certain functions, certain integral functions can have a special treatment. Could be nicer, This I can do a nice trick. Could be very nice, This one is equal to. This one is equal to sine x plus x, sine x plus cosine x minus cosine x, right? Dx. Okay, that is a trick. The trick number 1. Okay, then this becomes a what? Integral, right? 1 minus cosine x, sine x, and plus cosine x, and dx. All right, then this integral is x, right? Minus integral sine x plus cosine x. Now, look at the denominator. The denominator derivative will be cosine minus sine. Cosine minus sine. This derivative is cosine. This derivative is minus sine. Now, I do have cosine. I don't have a negative sign. So I just put sine x, negative sign, and the plus sign. See? Still equal, right? So this one is equal to x minus, this is sine x plus cosine x. And this becomes the derivative of sine x plus cosine x. And negative becomes negative, right? Negative plus, because negative. This is a sine x plus cosine x dx. So this becomes log, this is natural log, right? Sine x plus cosine x. And this is original given integral, right? Therefore, my I is equal to half x minus plus cosine and plus c. See, very nicely done. Okay, now here I'm not using let the u be this and so on. I have a special. Well, I have a video showing that for simple substitutions you can omit the u business. Just directly writing this. So if you want some detail, you can see my videos. The titled "Forget U Business." Let the u be this, then the du and so on. After finishing, you put a u back, with x. But here it's just straightforward without interruption. Okay, this is method 4. Method 4. Okay, method 5. The last method. You know, these methods are the special treatment for the special case. You know, because it depends on the function given. Okay? But the first 3 methods are more general. You can apply, well, commonly used. But this is very special treatment. You know, I call this as I1. I call this I2 is integral cosine x dx, and sine x plus cosine x. This is I1. This is I2. Then I1 plus I2 will be this, right? Because numerators and cancel out. So this is x plus c1. Okay, very easy. And I2 minus I1. This would be sine x cosine x, right? And this will be minus 2. This is I2. This is negative I1 sine x, right? dx. So this one is exactly the denominator derivative. You know, this is the derivative of a denominator, sine x plus cosine x, right? So this one is equal to log sine x plus cosine x plus c2. Now we're looking for I1, right? So I1 is a 1/2 I1 plus I2 minus I2 minus I1, right? That is I1. So I got I1. So this means simple. I1 plus I2 is x, right? It is x log sine x plus cosine x plus c. Yeah. I2 is okay. So it's nicely done. This is the best method, right? But it's a little tricky. Let me summarize again, okay? When you deal with integral function, the sine, cosine, you have basically you can do directly without any treatment. That is one possible way, and you can use let x be tangent half, or t be tangent half x, right? That's another basic technique for dealing with sine and cosine. Or you can use complex number, as I've done in the first 3 methods. But for a particular integrand function, sometimes you have a nice treatment. You know, this is based on your knowledge of trig functions and the integration techniques. So this example, 5 methods, is a very good example for those who taking calculus course, you know, to practice the different techniques of integrations. Okay, it's nice. Thank you for your watching. See you next time.